So hello everyone. Today's topic of the physics lecture will be um, torque and rotations. So here is the first problem. Yeah, you can read it for yourself and try it. I'll give you um, like 2 minutes to do it because this one isn't that hard. So yeah. Okay, that's about 2 minutes, so let's get started on the problem. Okay, so the first thing to realize is that if you consider this entire system, like obviously there are going to be forces along these struts here, but they are all internal forces if you consider this entire thing as a system, and the only external forces are this normal force, which we can label call NG. Sorry, this other normal force, which we can call NA, and this force from W, which is obviously just W. Okay, so yeah, now you can see that there's these forces are going to have a torque on the entire system. So if we take A to be the pivot point, then obviously NG, the torque is NG times the distance of the force to the pivot point, and this is just 18. And this has to cancel out the torque from W because the system is at rest. So this is W, and that distance is 12. So then that means NG is equal to 2/3 W. Similarly, if we take G to be the pivot point, then we get NA times 18 is equal to W times 6. So NA is just equal to 1/3 W. Okay, now we want to find the forces in B, D, and DE. So what we do is we take parts of this system and look at them individually. So first, um, let's look at the system. Um, yeah, let's look at this AB, this small triangle ABC here, and I'll draw it again here, ABC. And yeah, if we take the pivot to be C, then um, there's going to be a torque from BD. Yeah, if you look, obviously the forces um, BC AC and AB are internal forces, so they won't have a they won't have a torque around the pivot C. So yeah, if we look at the triangle ABC, then obviously there's external force from BD, which is either pushing or pulling on B. We'll figure out which direction it is later. And there's also NA here. So yeah, these are the only two external forces. So we can use that to try and balance the torques. And we get that NA times the length of AC, which is 6, is 6 NA, and this is equal to FBD. And here we can see that this the force or the torque from BD has to cancel the torque from NA. BD has to go this way in order to make it rotate this way, because NA makes it rotate this way. Okay, so yeah, now the torque from BD is just equal to FBD times this distance here. And yeah, this is yeah, pretty standard stuff. So this is obviously from Pythagorean theorem. This is a 3, 4, 5 triangle. So this is 4. And then we just get that FBD is equal to 2/3 NA. And since we found that NA is equal to 1/3 W, then this FBD, FBD is actually equal to 3/2. 3/2 NA, my bad. And so since NA is 1/3 W, then this is just 1/2 W. So that's FBD. That was the first part of the problem. Now, if we want to find the force in DE, that's a bit more complex. Okay, so now let's look at the system ABDC here, which is like this, ABDC. And yeah, if we now let's just try to balance the torques on this around the pivot A. And so there's a DE here and a DF. Okay. So if we look at the system pivoting around A, then we can see that the only external forces are from DE and DF. And yeah, the torque from the force in DF is obviously just FDF times this length from here to here, because it's the pivot A. And that is obviously just 4 again from the Pythagorean theorem, and this is equal to FDE times this distance if we extend it. It makes a perpendicular. Okay, so yeah, this problem to finding this distance isn't too hard. Just use similar triangles, because this is still a 3, 4, 5 triangle, and we get this should be equal to okay, this diagram isn't the best, but this is 5 and this is 3, so that and since this total length here is 12, that should be this length will be yeah, this, like, since this angle corresponds, this length is the 4 side of the 3, 4, 5 triangle, so then it should be 12. So this should be 12/5 times 4. Yeah. So then, yeah, now we can figure out the FDE in terms of FDF. So FDE is just equal to 5/12 times FDF. Okay, now we still need to write FDE in terms of W. So now what we do is we look at EFG as a system now. And so if we do that, EFG, again, this time we take the pivot as point E. So DF is here, and there's an NG here, and FDF and NG are the only two external forces on the system because everything else goes to E. And so now we just cancel out the torques again. And FDF, the distance here is 4, so it's 4 FDF is equal to, and the distance from E to the NG vector is just 6. So it's 6 NG. So then FDF is just equal to 3 halves NG. And since NG we found is equal to 2/3 W, this is just equal to W. So now we can easily find that FDE is just equal to 5/12 W. So that's the answer to the problem. And does anyone have any questions? Okay, that since it looks like no one has any questions, let's move on to the next problem, which is this. Here, let me copy and paste it here. So we have a horizontal thin rod of mass and length L is on one end of the support and suspended by a string on the other end. So it's like this. This is the rod and here's a string suspending it. And so it asks, what is the force F exerted by the rod on the support, which is here immediately after the string is burned. So this problem is like pretty easy. And it's like one that a lot of people just find because I think it's from wait, no, never mind. Anyway, it's a pretty easy problem, so I'll just get right into explaining it, especially since the next problem is like pretty long and hard. So yeah, so first we just draw the free body diagram here. Obviously there's force mg on the center of the rod, and there's also a force F by the support on the rod, which, and this F is what we're trying to find later. Okay, so after the string is burned, so we don't have this, this end, the acceleration of this end is 0. And this is pretty intuitive. If you think about it, like if you just like try to imagine this, it's pretty clear that the moment the string stops supporting the rod, it'll start moving. Like there's an acceleration on the center of mass and like the other end, but this end supported by the rod doesn't move, and that its acceleration is 0. So how do we get this acceleration to be 0? Well, the center of mass has an acceleration, and since this rod is also rotating, yeah, the rod will rotate this way, which means that this end is going up, and that should cancel out the downwards acceleration of the center of mass so that the net acceleration at this point is 0. Okay, so the acceleration of the center of mass is just equal to F over m, and F is equal to mg minus F over m. That's g minus F over m. And then when the rod rotates with an angular acceleration of alpha, then this end of the rod is going to be moving up at with an acceleration of alpha times L over 2 because it's rotating around the center of mass, and the distance from this end to the center of mass is just L over 2. And yeah, so now to find alpha, we have alpha is equal to the torque over the moment of inertia. And of course, the torque here, this we're looking at it, the rod rotating around the center of mass. The force is F going up here, and the distance from the force to the pivot point is L over 2. So that's FL over 2. And the moment of inertia, since it's rotating around the center of mass, the moment of inertia is 1/12 mL squared. So this is just equal to 6F over mL. Yeah. So then alpha times L over 2 is just equal to 3F over m. And we have that this has to be equal to ACM. So then we have G minus F over m is equal to 3F over m. So 4F over m is equal to G. So this just means that F, the force we're trying to find, is just mg over 4. That's the answer. That was a pretty easy problem. Does anyone have any questions about this problem? Okay. Since it appears that no one has any questions, let's move on to the third problem. And our third problem here is from use of flow, so it's pretty hard. So here, let me copy and paste it here. Okay. So okay. Let me paste the rest of the problem. Okay, so here is part A of the problem. We have a domino on a table with these dimensions, and it can rotate but does not slide. So first, we give the domino a sharp horizontal impulsive push with a total momentum of P. And part 1 of A, it asks what height h above the table is the impulse P required to topple the domino smallest, and then it asks us what is this minimum value of P. Okay, so for part 1, obviously the torque is larger the further we get from the pivot point. So the domino is going to be pivoting around here, and if we like apply a force anywhere, like here, then the distance is just this. And since obviously the larger the distance, the larger the torque. And so if we can get the torque and so then obviously we can make the impulse P smaller just by making this distance larger, and the answer is obviously just this largest possible distance, which is h is equal to h, the height of the domino. So that's really easy. And part 2 is a bit harder. So yeah, so as I mentioned before, the domino will pivot around this left edge here. And the moment it begins to fall is when the center of mass passes across this line. So if we draw a vertical line from the pivot point here, then it should pass the center of mass and this other corner. And the moment the domino moves beyond this line, then it falls. So we just want to delivering an impulse at height h. We just want the impulse to be large enough so that it can get to this state. Okay, so yeah, we know that this impulse is just I I omega 0 is just equal to pH from the impulse momentum theorem. I think that's what it's called, yeah. Or no. Okay, so anyway, yeah, it's called angular impulse theorem actually, my bad. But it's just that I omega 0 is equal to pH. And this is analogous to like everything else done in rotation, such as the A is equal to alpha R. It's just the same thing. You multiply the impulse by the length, and it gives you this angular impulse, I omega 0. Yeah. Okay, so now, yeah, so first we want to find I. Because the domino is rotating around this axis, I is going to be a bit tricky. Yeah, so first we can use parallel axis theorem. It's equal to ICM plus MR squared. So basically, if we were to take the axis through the center of the domino, then that would be ICM. But since we're here, we have to add another MR squared, and that's just parallel axis theorem. And this is ICM plus M, and this R is equal to root H squared plus D squared over 2. So that's just H, when we square it, it's just H squared plus D squared over 4. And so now, now we just need to find ICM, which is the moment of inertia for a domino or like a rectangular slab like this. Okay. So this ICM is equal to what we have to integrate. So let's say integrate x from negative t over 2, and that's like this width, to the other end, which is t over 2. And when we rotate, we don't have to look at it. Wait. Okay. Yeah, we don't have to look at it three-dimensionally. It's basically just, I guess, two-dimensional in when we're calculating the moment of inertia here. And so basically, it's just a bunch of thin rods like this. And we can use parallel axis theorem again for that. So the moment of inertia of this thin rod would be 1/12 m h squared. So h squared for now. And we have to add another value because of parallel axis theorem again. Because when we have a rod like over here, there's still this distance, and this is x, which is what we're integrating over. So then from parallel axis theorem, that would be a plus mx squared, so plus x squared. And then we multiply all this by dm, since the mass of each one of these small rods is going to be an infinitesimally small mass dm. And so we integrate this. The 1/12 h squared part is constant. So when we, that would just be 1/12, and then the total mass m times h squared plus, and when we integrate x squared, it becomes 1/3 x cubed. And we're integrated from negative t over to t over 2. And this small mass dm, we know, is just m over t, because it's basically, there are t of these infinitesimally small rods, and they add up to be mass m. Okay, so yeah. When we take the second 1/3 x to the x cubed part, it just becomes 1/12 mt squared. So this is just equal to 1/12 mh squared plus yeah 1/12 mt squared. Yeah. So now going back to this I is just equal to this plus mr squared, or mh squared plus t squared over 4. So this is just 1/12 mh squared plus t squared plus 1/4 mh squared plus t squared. This we can simplify to 1/3 mh squared plus t squared. Okay, so going back to this I omega 0 equals pH, we can now write that omega 0 is equal to pH over I. And yeah, this is equal to, of course, pH over this is 3 pH over m times h squared plus t squared. Okay, so now basically we found the angular velocity of the domino, like its rotation after giving it the impulse, is this omega 0. So when it rotates, it's going to have a rotational kinetic energy. And we also notice that the center of the mass lifts up from originally being somewhere here to here. So that means that the potential energy increases. The potential energy of the domino increases, and this potential energy has to be equal to the rotational kinetic energy, because basically the impulse gives it energy, which causes it to rotate, and this causes it to lift the domino to lift off the ground enough to topple over at the point that I mentioned here in this vertical line where the CM passes the pivot point. So basically that means since the rotational kinetic energy is just 1/2 I omega 0 squared, this has to be equal to the change in the gravitational potential energy. Okay, and this is equal to mg times the height difference. So originally here, this would be h over 2. And when it rotates, now this height is root h squared plus t squared over 2 minus h over 2. Okay, so this means that I omega 0 squared is equal to mg times square root h squared plus t squared minus h. And yeah, so now we can plug in our value for omega 0. I omega 0 squared is just equal to pH times omega 0, which is of course 3p squared h squared over m h squared plus t squared. Okay, so now this has to be equal to mg times square root h squared plus t squared minus h. And yeah, okay, so now we can just solve for p. Then p squared is equal to, okay, yeah, it's equal to m squared g times square root h squared plus t squared minus h times h squared plus t squared all over 3h squared. And remember that this, we found earlier in part 1 that this big H is just equal to H in the case that gives us the minimum value for p. So this is just equal to 3h squared over small h squared. Just 3h squared. Okay, so now, yeah, it's pretty easy to find p. We just take the square root and we get that p. It is equal to m over h times square root of g square root h squared plus t squared minus h times h squared plus t squared all over 3. So that's the answer. P is equal to this. And so that's the answer to part 2 of this useful problem. And with that, it looks like we're out of time. It's 6:02 already. So does anyone have any questions on this or any of the previous problems? All right, sis. It looks like no one has any questions. Then that's it for today. And thank you all for coming.